Okay, folks, welcome back to part two of electrochemistry, where we're going to go over balancing redox reactions. So reactions that specifically oxidize and reduce the elements that are involved. Okay, so unlike other balancing that we did at the beginning of the year in September, we're not just going to balance all of the atoms, or even when we were doing thermodynamics, we were balancing the heat or the energy across the different reactions. Now we also are really interested in balancing the charge and the movement of electrons. So in all of these reactions, we're going to change the oxidation states of the different molecules involved, as well as potentially the species of molecule. And there are special rules for how we're going to go about that. Okay, these really rely on two fundamental concepts. So one, that for every oxidation reaction, there's a reduction reaction happening at the same time. So if something is going to be giving up electrons, something else is going to be picking them up and taking them. So we can use that to split the reaction that we're trying to balance into two half reactions. It's going to make our lives a lot easier. Secondly, we know that these are going to be carried out in solution. For the ones that we're interested in for now anyways, we're looking at aqueous solutions, so things that are happening in water, and whether or not the water is acidic or basic is going to determine exactly where we find our extra hydrogens. So when we're balancing hydrogen, and from that we can also balance the charge. Okay, so on your handout you've got a list of steps that I really strongly suggest you go through each one of these steps as you do all of the practice problems that are in the textbooks, because this is essentially an algorithm that's going to lead you to the right result as long as you take each one of these steps in turn. Okay, I could just read them out, but I think it would be more useful if we skip right to the first example and we just try that first. Okay, so on your sheet, okay, let's see if my screen is going to let me do what I need it to do. Here we go. So on your sheet, you've got it written. So we're going from copper metal with silver ions in solution to copper 2 ions and silver metal. So you can imagine this setup being like you've got a beaker with some silver ions from silver nitrate or whatever other salt you put in there, but there are 3 silver ions in the solution, and you just set in a plate of copper metal. So what this reaction is suggesting is that over time, the silver ions in solution are going to be replaced with copper ions, and the surface of that copper bar is going to be coated in silver. So any kind of silver plating or gold plating, this is the kind of idea of how we might get there. Okay, so we go back and refer to your sheet for the steps for balancing redox reactions. Step one is to split the reaction into two half reactions. So what that means is that we're going to take, say in this instance, we'll take copper, metal, going to copper 2 ions. So this is going from copper 0 to copper 2 plus. So this is our oxidation reaction. And it's really clear here. It may not be clear in other cases. You'll have to go back and think about the oxidation state of each of the atoms. But obviously, whatever's left over is going to be a reduction reaction, and this is going to be the silver ions turning into, there we go, silver metal is our reduction. Okay. Step two is to balance every element that is not oxygen or hydrogen. So those ones are special because of how they're going to participate, say, with the water, the solution itself. But we want to balance everything else here. So, okay, we're going from 1 copper atom to 1 copper atom, no change. 1 silver to 1 silver, so we can call step 2 done, okay? Step 3, we're going to balance oxygen by adding water to the side that needs the extra oxygen. Both sides of both reactions have 0 oxygens, so there's nothing to do there. So step 3, check. Step 4, likewise, we don't have any hydrogen for this one, so we're just going to leave it aside until the next example. We'll come back to it. We pick up again at step 5. So for step 5, we want to balance the charge of each of the sides of each of the 2 half reactions. So you see on the copper one, the left-hand side is neutral, so copper 0. On the right-hand side, copper 2 plus, we need to get that back to 0. So we're going to add 2 electrons. Okay, 2 electrons. So now 2 electrons, 2 negative charges, plus the 2 positive charge on the copper, and we're back to neutral. Second line, we're going to do the same thing. So now we're adding an electron onto the left-hand side of that equation with the silver ion to just turn it into silver metal. And this makes sense. This makes sense with how we think about the oxidation or the reduction reaction happening. The copper is being oxidized, it's giving up electrons, so those are in the product side of that equation. And the electrons that are coming in on the silver side, this is on the reactant side of the equation because we know they're picking it up in order to turn into silver metal. Okay, so we balanced the charge on each of the things. Our final step is going to be to sum these back into one single balanced equation. But the real kicker is that we don't want to see any electrons when we have our final balanced equation. So what this means is that we have to make sure that the electrons can cancel out on either side. In our case here, we have 2 electrons on the right-hand side from the copper, but only 1 coming in on the left-hand side for the silver. So in order to correct that, we just multiply through by 2 on the silver side. And so when we add it all together, we can just cancel out the electrons. This is always going to be the goal of these balancing projects. Cancel the electrons so that we end up with copper metal and 2 silver ions go to copper 2 plus and 2 silver metal, okay? And for full marks, you're going to want to put down all of the states of matter, aqueous copper and solid silver, just because more than almost other things that we've talked about so far in terms of solution, the state of the matter really is important. It's going to tell us or inform us whether or not the electrode weight is going to change, how the concentration is going to change in solution. So it's something that we want to track, so be sure to write it down. Okay, and now we can flip the page and we'll go on to our second example. So here we're going to pick up some oxygen and some hydrogen in the form of nitrates, and ammonium. All right, so step 1 is going to be the same step 1 that we had before. We want to break this into 2 half reactions. So the oxidation reaction, again, is quite obvious. It's going to be zinc 0, zinc metal, is oxidized to zinc 2 plus. And so that only means that our nitrate will be reduced to NH4, ammonium. So this is our oxidation and reduction reaction. Okay. All right, so step 2, now we have to check the balance of every element that is not oxygen or hydrogen. Now we do have some oxygens and hydrogens. We're just not going to worry about those for now, but we can check the zinc. So we have 1 zinc and 1 zinc, we're good there. The nitrogens, 1 nitrogen to 1 nitrogen, still no problem there. So step 2, we can just call good for this example. Step 3, so this is something that we did not do last time. We're going to balance the oxygen by adding by adding water onto the side that needs the extra oxygens, okay? So on that second line, for the nitrate to the ammonium, there's 3 oxygens on the left-hand side, so we need to add 3 oxygens onto the right-hand side. We're going to do that by just adding 3 water. Okay, so now we have 3 oxygens on both sides, so those are balanced. Step 4, we're going to balance the hydrogen. So balancing hydrogen now is where we want to pay attention to what it says in terms of acidity or basicity or alkali solution, because that's going to tell us where the source of the hydrogens are, okay? The source of the hydrogen is always going to be the acid in the solution. In an acidic solution, we have the hydronium ion. So that's going to be the source of our hydrogens. And we need to pick up as many hydrogens as we have on the right-hand side. So we have 1, 2, 3, 4 with the ammonium and 6 waters. So that's 10 overall. And now you're going to say, well, okay, that's actually 30 hydrogens and now 10 extra oxygens that we have to what? Go back and balance? Well, we can do that. But what we're actually going to do is add water onto the other side so that we are, actually, let's just do that explicitly. So if we add on 10 waters onto the other side, then you'll see the only thing we really added is 1 extra hydrogen onto the side that needed the extra hydrogen. These extra waters just cancel out the rest of the hydronium molecule, okay? So obviously we can add that side up and we get 13 waters onto the one side, 10 hydronium on the other. And at the end of the day, they are all balanced, okay? You can stop the video, of course, and just prove it to yourself if you want to check how this all works, but you can also just believe me for now, and that's how we're going to play it. Okay, so all of our atoms now are balanced. We have balanced everything that's not oxygen and hydrogen. We've balanced the oxygen and we've balanced the hydrogen. So the only thing left for us to do is to balance the charge on both sides. So we're going to do that in exactly the same way that we did before. So we have zinc 0 going to zinc 2+. So we need to add 2 electrons onto the oxidation reaction. And how many electrons are we going to have to add onto the bottom one? So find out what the charge is on both of the sides. So let's say on the left-hand side of the reaction, we've got 10 positive charges, -1, so this is going to be +9 overall on that side. On the right-hand side, we've got +1, and that's it. So +1, and that's all. So what we have to do, again, we don't have to get them to 0, we just have to get them balanced. So we have to bring down the left-hand side of this equation down to -1. So we need to add 8 electrons. Actually, I should maybe just do that in red, I guess, for consistency's sake. Let's see if I can erase. Not really, but that's okay. It's still in blue. Okay, +8 electrons. And now this is going to be +1. And we have everything balanced. Okay. Obviously, we don't have balanced electrons between the two half reactions. So that's going to be our final step before we sum them back together. So we've got 8 electrons on the left-hand side of the bottom reaction, 2 on the top right-hand side. So we'll just multiply the whole thing through by 4. And this is going to be 8. So now we'll be able to cancel the electrons on both sides. And that's what we'll do. So we want to sum this whole thing up so we can cancel out our electrons completely. And what are we left with? We have 4 zinc. And we have 10 H3O plus a nitrate. And we're going over to ammonium plus 13 waters. Okay, and we would put through, of course, all of the little subscripts for, that says silver, but that's fine, you get what I'm trying to say, aqueous. aqueous, put through all our subscripts for the states, and we're done. That's the final balanced reaction, okay? So again, now looking at that just on the screen, it looks a little bit busy, but it's about taking each step through at a time and ending up with a balanced reaction in terms of both charge and matter. Okay, and before we finish, we're going to do it one more time in basic solution now. Okay, and so again, now we won't have the acid for a proton source, but we will have an acid, right? So in a basic solution, we have an excess of hydroxide, so that's our base. It still has its conjugate acid. The conjugate acid of hydroxide is water. So we're going to use water as the acid in this case, and that's going to be the source of the protons, or the extra hydrogens, okay? So let's take this through step by step as well. So we have silver with hydrogen sulfide and chromate ion going to silver sulfide and something else. Okay, so let's work this one through. If it's not obvious which one is going to be the oxidation and which one is going to be the reduction, don't really worry about that because it's going to show up as we work our way through. But we do want to make sure that we're getting all the elements we need on each of the two lines. So just as a starting point, let's say we have the silver and the hydrogen sulfide going to Ag2S, so the silver sulfide, because again, that has the silver and the sulfur that we're going to need for the final, for the product. So let's keep those together, and we'll keep everything with chromium together, and that'll be our second row, okay? So CrO4 2 minus to Cr, so chromium hydroxide, okay. Okay, and at this point, it might be worth it to you to try to think about which one is being oxidized, which one's being reduced. The easiest way that I would do it personally is to just check out the oxidation state on the chromium. So here you've got a total charge on this ion is -2. There's 4 oxygens, so that's going to be -8 overall. To bring it back up to -2, we're going to have a +6 on the chromium. And over on this side, we know that the hydroxide's a -1. There's 3 of them. So for that to be a neutral molecule, this is going to have to be +3. So now you just think, okay, well, is that oxidation state going up or down? In this case, it's going down. So this is the one that's going to be reduced. And by extension, this silver is going to be oxidized. Okay. Again, that's going to show up naturally as we go through it, just because we'll be able to check which side we push our electrons onto. But just for extra practice, there you have it. Okay, so let's go back over to the pen. Maybe, here we go. Okay, so that was step 1, break it into half reactions. Step 2 is balance everything other than oxygen and hydrogen. So looking across the top line, we start with 1 silver and we end up with 2. So we'll need to add a second silver into the reactants. 1 sulfur, 1 sulfur. Hydrogen we're not worried about yet. On the bottom line, chromium is good across the way. Oxygens and hydrogens we're not worried about. Okay, so that's step 2 done. Step 3, we want to balance out the oxygen. No oxygen in the top row, so we don't have to worry about it there. Bottom row, what do we got? We got 4 oxygens on the left-hand side, 3 on the right-hand side, so we'll need to add in 1 water, because that's going to give us 1 oxygen atom, okay? Hydrogen we're not worried about yet. So now we have 4 oxygens on the left-hand side, 4 on the right-hand side, so oxygen's balanced. All right, let's go on to balancing hydrogen. And on the top row, there's one hydrogen on the reactants for the silver sulfide and none on the products. So we're going to add the acid to the side that needs the hydrogen. In a basic solution, we're not going to have any hydronium. What we're going to have for an acid is water. Okay, that's going to be acting as the acid. And to get rid of everything that isn't that extra hydrogen that we're really after, we're going to add on the same number of hydroxides onto the other side. Okay, so that leaves us, if we took water and just subtracted out no and an H, it would just leave us with the extra hydrogen that we were looking for. Okay, so we make sure that we had the same number on both sides. And let's check out the second line with the chromium. So no hydrogens on the reactant side. On the product side, we have 1, 2, 3, 4, 5. So we'll need to add 5 water, 5 H2O. And then we also need to add on 5 OH negative onto the products, just to balance out the rest of it, okay? And all we're left with is the additional hydrogens that we needed in the reactant side to make this work. Excuse me. Okay, and now we're ready to balance the charge on both of these sides. So what do we got? Let's look at the silver line. So we've got one negative charge here and another negative charge on the hydrogen sulfide. The ones on the product are neutral. So let's add on 2 electrons onto that top row to balance the charges there. Bottom row, we've got -2 on the product, or on the reactants, and -5 on the product side. So we need to add in 3 electrons to the reactants to make sure that the charge balances across the half reaction. Okay. So with that, we've got let's look, 2 electrons on top, 3 on the bottom. Our final act is to sum these back together. We want to make sure that we cancel out all of the electrons. So in order to do that, we're going to have to multiply the top row by 3 and the bottom by 2. So that gives us 2 OH negative. This is going to be 4 silver, 2 hydrogen sulfide. Now we have 2 silver sulfide, 2 water, and we'll have 6 electrons up here. Bottom row, we're going to have now multiplying it by 2, so we end up with, again, 6 electrons. This is now 10 waters. What are we doing? Multiplying by 2. Oh, we were multiplying up here by 3, weren't we? Yes, we were. Okay, so that's going to be 3s all around, so 6s. Just getting a bit of a mess. 3, 6, 3, 3, 3, 6. Okay. Okay, now we're good. And going through by 2, do 2, 2, 2, 2, 2. Here we do 2 of these guys, and we got 10 hydroxides. So yeah, sorry for the little mistake there, but I'm not going to go through and redo this whole video just for mistake. So we got multiplied by 3s on the top row, 2s on the second row, and at the end of the day, we have 6 silver plus 3 hydrogen sulfide plus 2 chromates. Okay. 2 minus, and 5 water. All going to 3 silver sulfide and 2 chromium hydroxide and 7 hydroxides. Okay, so there you have it. So there's the balanced reaction in basic solution. All the charges are balanced. We've included now the water and hydroxide in there, again reminding that the water is acting as the acid in this case. and everything else should be complete. Okay, so I think we'll leave it off there for this one. We'll pick it up next time with the disproportionation reaction, just to do one more review of what this can look like in a case where the same reactant is going to be both oxidized and reduced. Okay, thank you very much for listening, and we'll talk to you soon. I wonder if that worked. Did that stop it?